If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started.
In this tutorial, we're going to talk about a very popular regularization technique in neural networks that's known as dropout. Let's start with an analogy. Let's say we have a team of professionals who are all practicing data science, but a team would have members with different strengths. For example, a particular team member says that I can do predictive modeling really well. Someone else says that I can do data wrangling. Another team member says that I can make good presentations. And there could be team members who are still trying to wonder as to what they can do, but they're not quite vocal about it. But it is very natural in a setting like a team, whether you're working on a project at work or you have a team, let's say we talk about sports, you'll have players with different strengths. And that seems to be the case here. Together, these people give an amazing output. But there could be situations when, let's say, the boss approaches someone else today saying that the guy who works on the data generally, who does the wrangling piece, is not available. So can someone else help me with that? Now, the fact is that not everybody is as good as this guy who specializes in data wrangling. Likewise, the person who was good at making presentation had to leave early, and the boss expects someone else to take a lead and make the presentation. While this might not be the core strength of the person who is expected to present now. And likewise, there could be any urgent requirement where just about anybody who's available can be approached. So the point is, if we specialize in a core area and the entire team depends on us, the day we are not there, the entire team will be impacted. So don't you think it will be better if the person who was very confident with predictive modeling also knows data wrangling and making presentations? Wouldn't it be better if the person who was good with data wrangling also knows predictive modeling and making presentations? And what about this? The person who makes presentations should also understand predictive modeling and data wrangling. Now, we are not saying that everybody can do everything. We are saying that we should have replacements. We should have a hierarchy that if level 1 is not available, somebody else is there to take care of it. It should not be in a way that the chain gets broken the moment a particular link is missing. And that's what we are trying to understand here. Now, how does it fit in the context of neural networks? Let's understand that. The motivation behind dropout is very straightforward. Whatever we do at the training stage is what we want to be able to translate to the test stage as well. It should not be the case that we do very good at the training stage, but we are not able to deliver the same level of performance at the test stage. And that, in general, is a concept of regularization. Dropout is a technique that helps us achieve that regularization. Let's say this is our simple neural network with an input layer, a hidden layer. We have 5 neurons here and an output. Now, you know, every neuron in the hidden layer serves a purpose. It does some tasks, and not all these neurons are identical. They specialize in a specific task. Now imagine if we choose to randomly drop 40% of the neurons from the hidden layer. If we're randomly choosing any 2 neurons out of 5, our network might look like this. So if you see, these 2 neurons are no longer participating in the network. There is no connection that's pointing to them or out of them to the output neuron. So these are not acting anymore. The entire responsibility now is shouldered by these 3 neurons, which are nicely connected. So the connection between the analogy and our example of neural network is this, that let's say the data wrangling expert is this one and the presentation expert is this one. Now, when they are not there, the other team members need to shoulder the responsibilities. And they will have to do that because overall the team still has to perform. You have to run your business. Now, it's not necessary that we choose specific neurons. It could be randomly done. You know that mostly we do mini batch gradient descent. So for each batch, we may drop a different pair of neurons. And this 40% was also just an example. It could be another 40% here. So in this case, these middle 3 neurons are intact and the extreme ones have been dropped. It could be any pair of neurons that we drop. Likewise, we can drop these 2, or maybe these 2, or maybe these 2. So by now you get the idea that let's say this is the network, and if we choose to drop 40% of the neurons, 40% of 5 is what? 2. If we choose to drop 2 neurons out of these 5, it can be done in 5C2 ways. Or 10 different ways. So in a way, you can imagine that this is our original neural network, but we are trying a mix of models. This is a different architecture. The second approach was a little different. More approaches like these, and they're all different in a way. If you've studied ensemble learning as a part of machine learning, in a way you're looking at multiple models here because these neural networks are not identical. But keep this in mind, this dropout is applied only at the training stage, not at the test or inference stage. And as a part of this exercise, every single hidden neuron would be more efficient. Now, another opportunity that dropout helps us overcome in neural networks is like this. So let's say we have multiple layers. We're just taking an example of one hidden layer, but there could be multiple layers. Imagine this is also a hidden layer, and we have all these connections going on. Now, the entire work that we are doing in neural networks, like updating the weights, etc., depends on how this y hat behaves with respect to the y, or the predicted value. Essentially, we are working towards reducing the loss. In the process, what happens is that there could be certain inefficiencies that we have built. For example, this neuron might be doing something wrong, which this neuron eventually fixes. But you wouldn't be bothered about it because end of the day, this problem that was created here was resolved here. And all you worry about is the end result. So in a way, it's like this, that this neuron says, I break it. And this neuron says, I fix it. And we say that end of the day, it doesn't matter as long as it's done. Now, this process is called co-adaptation. What's inefficient here is that a particular neuron is not doing what it's supposed to do, but someone else is compensating for it. However, when you do dropout, imagine when this neuron that fixes the problems passed on by this earlier neuron is not there. Don't you think that day the outcome would be affected? Because the neuron which was responsible for fixing the errors here is no longer present. And now this neuron would somewhere be caught. Dropout also helps you fix this issue. So any dependency associated with the neurons dropped will have to be trained separately now. Now, one minor piece that you want to understand, as I said, dropout is applied at the training stage. At the inference stage, we have all the neurons. So one fine nuance that you need to know is that, so all these variants of dropout, as we proceed with multiple batches, were receiving 3 inputs in our case. But at the test stage, when we don't do dropout, you'll be getting 5 inputs. So to address this, most of the packages take care of it internally. What they do is they scale up the inputs at the training stage by 1/1 minus the dropout rate. So if our dropout rate was 40%, then the adjustment or the scaling here would be 1/1 minus 0.4, which will be 0.6. And that comes to the denominator. So eventually 0.6, a fraction in the denominator. So it scales up the inputs at the training stage itself. This is another nuance that you need to be aware of. While most of the libraries take care of it, it's just a good to know piece. That's pretty much about dropout. It's a straightforward concept, but it's an important concept. And it does make a lot of difference when it comes to regularization.